Alright, so in this lesson we're going to take a look at what are called double bonds. Now in a previous lesson we looked at single bonds and what happens when you form lone pairs of electrons. All of those come from hybrid orbitals. This double bond is going to come from not only hybrid orbitals but in unhybridized p orbitals. Double bonds are a combination of sigma bonds and what are called pi bonds. Alright, so we're going to talk about double bonds today, but I want to review just a little bit about single bonds because it's going to apply to what we're doing here. Okay? So we spent quite a little time, the entire class period really, going over single bonds and lone pairs and various things like that. So I just want to remind you that all single bonds are also sigma bonds. All single bonds are also sigma bonds. All lone pairs and sigma bonds always come from hybrid orbitals. All lone pairs of electrons and sigma bonds always come from hybrid orbitals. What we're going to talk about today with double bonds are pi bonds, which do not come from hybrid orbitals. Okay? So the pi bond that's part of the double bond does not come from a hybrid orbital. We're going to make a combination of hydrogen, carbon, and oxygen. Okay, we're going to be putting together hydrogen, carbon, and oxygen. We're actually going to have two hydrogens in the combination we're going to have here to look at this double bond. Okay, this is a molecule called formaldehyde. We've worked with that a little bit before. We're going to look at it a little bit more differently now, but some of this will be review, so we can kind of bring you forward here, tying all the stuff you've learned before to what we're doing today. Let's look at how we would hybridize both the carbon and the hydrogen here. Let's do it first with orbital notation. So if we have the unhybridized form of carbon and it's the orbital notation of that unhybridized form, the orbital notation looks like this. Okay, that's unhybridized. Okay. Oxygen looks the same, except that we've got some additional electrons, two more electrons. And remember, whenever you get to a sublevel with more than one orbital, you put one electron on each orbital, and then if you need more than those electrons, then you can pair up, always starting from the left. Okay? So this is the orbital notation for carbon and oxygen. Hydrogen is simply, has just one electron. And these are arrows, up and down arrows. Okay, I use half arrows just because it's faster. Sometimes they're called fish hooks. Now, this hybridization that we're going to do today is not going to hybridize all four valence orbitals. Remember, all the orbitals, all the sublevels in the highest energy level, that's called the valence level. Those are called valence orbitals. When we're hybridizing all of them, we made S and these three P's into what is called an sp3. You could say it's an spp hybrid, but we call it sp cubed just because it's easier to write. But today we're going to leave one p orbital unhybridized. In order to make a pi bond, and a pi bond is required for a double bond, one p orbital has to be left unhybridized. So it's going to look something like this. Then one S and two P's get hybridized. That means our new hybrid here is going to be SPP, or an easier way to write that is SP squared. Okay? But the last p orbital down here is not going to be hybridized. Now, if you recall, when we hybridized all the s and p orbitals in the valence level, we put one electron in each of the orbitals and then went back and paired up if necessary. We do the same thing here, only we're not going to make p something separate. It's going to be kind of like part of the same filling order for electrons. Since I have 1, 2, 3, 4 electrons in the valence level, I'm going to put them in one in each of these orbitals. Okay? anytime you have to have a pi bond, you have to have p orbitals that are not hybridized. So if I have one pi bond, that's one p orbital unhybridized on each atom. If I have two pi bonds, that'd be two p orbitals unhybridized. Okay? So when we get a little further along, I'll kind of go back to that. It should make sense then, okay? And so the oxygen is going to be done exactly the same way. We have that 1s orbital that just doesn't change. We're going to have a spp or sp squared set of orbitals. 1, 2, 3 of those. This, and this gets hybridized. That one does not get hybridized, so that remains 2p. But we fill all four orbitals as kind of like one thing. Okay, so we have 2, 4, 5, 6 electrons. We put 1, 2, 3, 4, 5, 6. Okay, so this is an sp2 hybridization if we're looking at it from the point of view of writing orbital notation. Okay? And then you got these hydrogens over here. Now what's going to happen is, in order to put together two hydrogens, the carbon and the oxygen, then, well, let's just write that out over here. Let's write all this out down here, and I'll show you where everything's going to go. So we've got two hydrogens. We've got our hybridized carbon, sp2 hybridized carbon. And then we've got our hybridized oxygen. We have one p orbital that's not hybridized. So when we share all these electrons then, in order for the hydrogens to have 2 electrons and the carbon and the oxygen to have 8 electrons in the valence level, then we can share this electron here. Those orbitals get shared. So it's not only the electrons that get shared in covalent bonding, it's the orbitals themselves. The orbitals get shared, and as a result you have what's called a sigma bond, or a bond period. Anytime you have a covalent bond, you're actually sharing orbitals. And so this orbital in the hydrogen gets shared with this orbital in the carbon. Okay? So I've got 2 more orbitals that are available to share. So this orbital can share with this orbital. We're going to combine orbitals together, overlap them, they're sometimes called, to form this sigma bond. But this orbital here that I didn't hybridize, the p orbital that I didn't hybridize, when they share electrons, that's not going to be a sigma bond. That's going to be a pi bond. Okay? So, all of these right here are going to form sigma bonds. Okay? When electrons are shared between hybrid orbitals, you always form sigma bonds. Okay, whenever electrons are shared between hybrid orbitals, you form sigma bonds. Here, we're not sharing between hybrid orbitals. The p orbitals didn't get hybridized. So whenever we share orbitals between unhybridized orbitals, and those unhybridized orbitals will always be p orbitals. Well, in this class they will be anyway. you form a pi bond. So the symbol is the same symbol used in math for the relationship between the diameter and the circumference of a circle. Okay? So if you recall from last week, hybridized orbitals we thought of those as being a single balloon shape, and they will continue to be. Okay? The hybridized orbitals like these will all be single balloon shapes. Okay, single balloons here. Okay, these hybridized orbitals we'll think of as being single balloons. The p orbitals, if you recall, we were originally doing the shape of orbitals before we did any hybridization. S orbitals were spherical, p orbitals were double balloons. Okay, so here's these two orange balloons I'm showing you here. That's one p orbital, and so these unhybridized p orbitals will remain as that double balloon sort of shape. Okay, at least we think about it that way. We're trying to figure out shapes here. Okay. When these single balloon shapes overlap, they form that cigar shape or wiener shape like we did the last time we were doing this. The double balloons do something different, and that's what I'm going to show you now. Okay? First, let's do, just so we're kind of bringing ourselves up to speed here with electron dot formulas and then Lewis formulas. Here's the hydrogens with one electron dot, one valence electron. Carbons have 1, 2, 3, 4 electrons in the valence level. 1, 2, 3, 4. Oxygens have 6, 2, 4, 5, 6 electrons in the valence level. So they look like that. Okay, so that's our electron dot formula, our electron dot formulas. And then we're going to share electrons to get to the Lewis formula. So these are going to share here. These are going to share here. And then we're going to share another pair between the carbon and the oxygen. And that's the only way to get this number of atoms, these types of atoms, to the valence level of 8 electrons. The valence level having 8 electrons. That octet we're looking for here. Okay, hydrogens only want 2 electrons, but carbon and oxygen want 8. Okay, in that valence level. So we go from there to get the Lewis formula. And for 2 shared pairs, you put them in this format, sort of 4 corners of a box kind of format or arrangement. Okay, oh, that should be a carbon, not an oxygen there. I don't know why I made it look like an oxygen. That's our Lewis formula, then, our Lewis dot formula then for this same molecule. All right. But now that's just a way of keeping up with all of the electrons. It's not the actual shape of the bonds. When we share just 2 electrons, we get a single balloon shape. So if here's our carbon atom here, I'm going to bring one of these balloon shapes, long balloon shapes, wiener shapes if you want to call it, or a long balloon sort of shape. Remember, keep those kind of short. Some of the balloon models, pictures I saw had balloon models that, oh man, they must have been 3 feet long. Okay, they're 8 or 9 inches. Okay, keep it short. All right, and here's the hydrogen, and the other one needs to be back here. There's the other hydrogen back there. So this one's coming out in front, that one's going back behind. Between the carbon and the oxygen, we have a single balloon shape here. There's the wiener shape. All right. But if you recall, the reason we put these electrons in these different orbitals had to do with the fact that pairs of electrons don't like to be in the same region. They can't be. Okay? The only reason you put 2 electrons in the same region is because they have opposite spins. Once you have 2 electrons with opposite spins, that's it. Everything else is kind of locked out. So pairs of electrons after that then are going to push apart. So we call it valence shell electron pair repulsion, VSEPR. Okay? So the second pair of electrons here needs to be in some region other than directly on this line between 2 nuclei. And the way we get that is we keep those 2 p orbitals unhybridized. P orbitals be 2 balloons like this and 2 balloons like that, and they're going to reach out to each other on 2 sides. It's kind of like this is the wiener and this is the bun, and we make a hot dog. Okay? So it's two parts. When we do a pi bond, it looks like it has two parts. Okay? But it's the same bond. So any bond directly on a line between two nuclei is a sigma bond. This is a sigma bond. There's the Greek letter sigma. This is a bond directly on a line between the two nuclei of these two atoms. This is a sigma bond. This is a bond directly on the axis or line between two nuclei. That's a sigma bond, okay? But this is not a sigma bond because it's not directly on that axis or that line between the two nuclei. Now sigma is that, and pi is that, okay? So this was a p orbital, this was a p orbital, and they shared this way to form a pi bond. So the pi bond is both this and this. Okay, that's all part of the same pi bond. So this is a shared set of p orbitals. P going up and down this way, and here gets shared this way. And the sigma gets shared here. There are two electrons here, one from the carbon, one from the oxygen. There are two electrons in this pi bond, one from the oxygen, one from the carbon. Each one of these bonds shares two electrons, just like the orbitals can have two electrons, because it is a shared orbital. Okay? A bond, a covalent bond, the sharing of electrons, is sharing orbitals. Okay? All right, so we also have lone pairs on the oxygen. Okay, those are not bonded, and those form that single balloon shape and just kind of stick out like that. Okay, one behind and one in front. Okay? So these are lone pairs of electrons. One here and one here. Okay? They're sharing two electrons in the sigma bond and two electrons in the pi bond. So that's four electrons shared between the carbon and the oxygen. We have to put each pair in a different region. We can't put them in the same space because they push apart from each other. Like charges repel. There's two electrons in this pi bond, going top and bottom. There's two electrons in the sigma bond. It's not that there's one here and one here. It's that they're both in these two parts. Just like there was a either one or two electrons in those unhybridized p orbitals. Okay? All right. So now this is this sort of bonding then, because I have to leave a p orbital alone that is unhybridized in order to bond in this way, this pi bonding form. That means I can only hybridize one s and two p's to get these three sigma bonds, or one s and two p's to get this sigma and two lone pairs. Okay, remember, let's just make sure we're clear. All sigma bonds, and sigma is that symbol right there, and also all, well, let's don't do that. All sigma bonds and all lone pairs of electrons. Come from hybrid or hybridized orbitals. Those orbitals might be sp3s, they might be sp2s like we're looking at today, or they might be sps, which we'll look at tomorrow. Okay? Pi bonds come from unhybridized or p orbitals. Okay? Pi bonds come from unhybridized p orbitals. Everybody got that? All right, so let's take a look at how you're going to make these models physically. The carbon and the oxygen in your balloon model you're going to make, the carbon and the oxygen in the balloon model you're going to make will be where the balloons are all knotted together. We won't actually make models of the carbon and the oxygen. They'll be the knots that hold everything together. We'll make a kind of a balloon over here, a round balloon over here where the hydrogens are located, as we did the last time we did this, when we did all those single bond stuff. Okay? When you make your pi bond, and when you make this sigma bond between these two atoms here, you need to start by putting a little bit of a knot in the end of your long balloon, because you need this part over here to tie everything together. Okay? Your pi bond balloons need to be roughly 1.5 times longer than the sigma bond balloons. In order for it to stretch around, okay, it's got to be longer than this. So if you make this about 8 inches, this balloon here has to be about 12, and this balloon right here has to be about 12. Now you can make this pi bond, this part and this part, all out of one balloon. So you'll knot the end, you'll make an 8 or 9 inch length, tie a knot, make another, I'm sorry, not a 12 or 15 inch length here, tie a knot, and another 12 or 15 inch length here, tie a knot, and that can go around it like that to make that pi bond. The sigma bond that you make in the middle here needs to have a little piece of knotted at the end so you can tie it up right here, and then you'll put a knot over here and you'll make the little hot dog or wiener shape. Okay? These out here are made the same way we made them last week when we had hydrogens on the end, where you blow up a round part at the end, tie a knot, and then make a 9 inch length sigma bond and tie it all together. The balloon that you're going to make your pi bond needs to have a knot at the end, and the balloon you make this sigma bond needs to have a knot at the end. Okay? Now, you want to make the color of this balloon different from the color of the balloon you're going to make your pi bond with. Okay? In fact, it would be better, so the pi bond can be one balloon. You know, you're going to make two sections of it. Remember, these bonds, the balloon you blow up to make this bond here, this half of the bond here, has to be 1.5 times the length of this. Okay? So if this is 9 inches, this should be 15. If this is 8 inches, this should be 12. Okay? Roughly speaking. Then I would make my two lone pair balloons over here two different colors. And I'd make the two sigma bond balloons over here. To the hydrogen's a different color, but the hydrogen can be the same color as you as that sigma bond. I kind of allow that most of the time. Okay, does that make sense to you? What we're doing? You ready to get started? All right, you can pair up. Okay, you can find a learning partner. All right, and work on these together to make one model. But just like last week, everybody's going to do their own individual model for homework.